Let's take a look at a pretty straightforward example. So as always, I would encourage you to pause the video and work through this by yourself, and then come back to the video for the solution. So what we want to do is we want to calculate all of our terminal currents, so that's our base, collector, and emitter currents, as well as our collector emitter voltage for the circuit shown below. We're told to assume the base emitter on voltage is 0.7 volts and our beta value is 200. We also want to find the power that's dissipated in the BJT. So here is our circuit. So we see we have this sort of more compact drawing scheme. We no longer have the full loops showing the batteries. We just have nodes with VCC and VBB. And so of course you can see the advantage of that is it's a lot cleaner. All right, so we're going to start by doing a KVL around our base emitter loop. And the reason we want to start there, sort of our game plan, is we want to find our IB. We're going to assume we're in our forward active mode. So then we can find our IC from IC equals beta IB. And then we can do KVL on our collector emitter loop to find our VCE. All right, so let's start by looking at this base emitter loop right here. So we can do KVL, and we can say our IB, so KVL and Ohm's law sort of combined in one here. We can say our IB is equal to the voltage across that 220k ohm resistor, which is 4 minus our VBE on, which is 0.7, divided by the resistance value, so 220k. All right, so I plug that in and I get in my calculator 0.015. Because I've left this in k ohms, that means this is going to be in milliamps. So we see this is a really small current of 15 microamps. All right, so there's one value down that we were looking for, IB. So again, we said we're going to assume we're in forward active mode, and we're going to come back and talk about how we know when that's true in a later video. But for now, let's just say we assume we're in forward active mode. So that means that our IC is equal to beta IB. So in this case, we're given beta is 200. We just found our IB is 15 microamps. So what that means is our IC comes out to be 3 milliamps. All right, so moving on, we need one more current. So our last one is our emitter current, I sub E. And regardless of what mode we're in, we know that our emitter current is always equal to the sum of our base current and our collector current. So we plug in values for that. We could also write this a little bit differently. We could say this is 1 plus beta times our base current, or we could also say this is IC divided by alpha. Pick which way you want to do it. All are going to give you the same thing of 3.015 milliamps. And so as we might expect, we see that our collector current and our emitter current are very similar. And later on, particularly in later classes, what we're going to do is oftentimes we can just approximate IC is equal to IE, and that's going to make our analysis easier without much loss of accuracy. All right, so now we have all of our terminal currents. So what we can do now is move on to our collector emitter loop. Now that we know IC, we can figure out the voltage drop across that 2k ohm resistor, and we can do KVL to figure out our VCE voltage. So let's do that. So we can say our VCE is going to equal that 10 volts on the top, our VCC, minus the 3 milliamps of our IC times the 2k ohm resistor for our RC, and that is going to give us a value of 4 volts. And so as we're going to see in later videos, because that is 4 volts, we can be pretty confident that we're in our forward active mode. The last thing that we want to calculate is the power dissipated in the transistor. So now that we know all of our voltages and currents, we should be able to do that pretty easily. So to use our complete equation, we can say that our base current is 15 microamps, so 15 times 10 to the minus 6 amps, times our VBE on, which is 0.7 volts, plus our collector current, which is 3 times 10 to the minus 3 amps, times our VCE voltage, which we found to be 4 volts. If we evaluate that, what we get is we have 1.05 times 10 to the minus 5th watts plus 1.2 times 10 to the minus 2 watts. So to put those in units that are a little easier to see, we have 0.0105 milliwatts plus 12 milliwatts. And so what we can see is, of course, this second term from our collector current is dominating. It's a lot bigger than that term related to our base current. So we can say that this is approximately 12 milliwatts. And so oftentimes we won't even bother calculating that term related to the base current because it's usually just going to be insignificant. So in this example, it's worth noting that we are looking at an NPN transistor. Of course, there are often also PNP transistors. We just don't have time to look at examples of everything, but if you do want to see an example with a PNP transistor, you can look at example 5.4, which is on page 305 in the textbook.